morning. It's currently 11 o'clock, which means it's math time! Except on days when it's 10 o'clock, 12 o'clock, 1 o'clock, whatever days chimes change and things. However, we're going to try and do some math challenge questions today. We're going to focus on the junior math challenge, which is years 7 and 8. However, that's not to... 8 and 9? 7 and 8? 7 and 8. But that's not to say the same principles won't apply and be useful to year 10s and 9s, because the math challenge... The questions on the math challenge are slightly different to the sorts of maths that people see on an everyday basis. I try and include that sort of thinking where I can, but it's difficult to get it in there. So what we're going to do is we're going to go through... I've got 5 questions lined up. I'm going to go through them. I'm also going to try and break them down and talk a little bit about what I'm doing and how I'm breaking the question apart, and show you that these questions I think is real maths, as opposed to sort of learning a skill and just practice, which is valid. This is where we don't know what skill we're going to need, and sometimes I feel that mathematics is too often I'm telling you what skill to use and then you're practicing using it, and that's not how the real world works. In the real world, you're not told, oh, this question, yeah, this thing you're going to do, you're going to need to do this. Now go and do it. Sometimes you'll come across a problem and you're just like, what? I need to work out what to use. So let's get straight into the intro, and then I'll go straight into explaining some of these questions. So, here we are with the first question we're going to look at. These are all questions taken from last year's UK Math Challenge, and in the description link I've given you a link to where this past paper is, and you'll notice these are questions like 5, 10, 15 and 20, I believe. I think I've got 4 questions for you. Now, what I always want to do with any question like this is break it down. So 16th birthday and 21st birthday and 3 times our age are the only bits of maths here. Second thing I always do is I abbreviate any names to their letters if at all possible. So when Aoife, I think, when Aoife was 16, Buster was 3 times her age. So we can write that information down straight away. Now, I wouldn't necessarily expect you to do this, but what you can do at this point is cross out that whole line. We've used it all. Everything we've needed from there is used. Now, that means that we can write Aoife when she was 21. Now, 5 years have elapsed. So 5 years must also have elapsed for Buster. And that is the reason we're going to go with Buster being 43. Okay, just checking I've gone live. That's the reason we're going for Buster being 53. Because when you're looking at these sorts of questions... Now, the good thing about the math challenge is it gives you 5 possibilities. So we know there's a strong chance we're right, but we also want to just check. So let's just check that. When Aoife was 16, Buster was 3 times her age. Is that true? Yes. On her 21st birthday, Buster is now 5 years older. So we've gone through and we're quite happy with that. And that is how that question works. And it worked because I took it apart. The second question. We're going to identify the key bits. The last digit of the smallest... Please remember, by the way, on all these questions, feel free to pause the video, have a go at the question, and then watch my explanation, because that's probably a better way of doing it than just going, oh, how did Mr. Harris do it? Maybe you don't use that voice. The smallest positive integer whose digits add to 2019. So, when I break this down, we're going to have a number that is and we want to know what the last digit of this number is, but when we add them all together, we get 2019. Now, this is the interesting bit for me, because this doesn't seem immediately obvious until we realise that the smallest possible number will have the least numbers in it, because it's this number 1000 is bigger than 999, because when it's got 3 digits in it, it's going to be smaller than 4 digits. It doesn't matter what those digits are, 3 digits is always smaller than 4 digits. Therefore, if the digits add to 2019, we want we want to clump together as many 9s. So it's going to be 9999, skip a few, 999, and then we've got an end number and a front number. So the next thing I do when I'm thinking about a problem like this is I go, well, which is smaller, 1999 or 9991? And I think it's quite obvious to people that that is smaller. Therefore, that tells me that the non-9 bit has to be on the front, not the end. And that's useful because that means if the end bit has to be the 9, that tells us that the answer is 9. Because it says what's the last digit of the number, and we can see it's going to be a number with lots of 9s. In fact, I went further when I was working this out earlier because I wanted to check I could do them all. And I realised that the 2016, because 2, I don't know if you know this trick, but 2 add 1 add 6 is 9. If it's in the 9 times table, they will add up to a multiple of 9. Therefore, when you add those digits, you get 9. We know that's in the 9 times table. Therefore, 2019 must have a remainder of 3. That means it must be 3. No. I think it worked out like something like 274 9s. It's a lot of 9s. But you could work that out yourself and it will end in a 9. So there you go. This question we broke down. Again, feel free to ask any questions in the comments below the video. If you're not sure how I got started, it's important to learn things like positive integer is just a whole number. That's all that means. It's to stop people trying to use decimals and things. So we're racing through these questions and we get a visual question. I like visual questions, especially when I've got my grid paper, which is square paper, and it's got this one here. All 4 L shapes shown in the diagram must be placed in the 4x4 grid so that all 16 cells are covered and there's no overlap. Each piece can be rotated or reflected before being placed and the black dot is visible from both sides. Now the thing I love about this question is actually there are only 4 possible places that we're checking. So it must be a multiple because if we rotate the whole grid or rotate your paper, it accounts for this one, these 4, these 4, and these 4. So we need to check which of these 4 places are possible. That simplifies it a lot. Let's take all these off and let's try them. Now, what I like is that if we was to draw a square, we know there's only 4 positions we're trying to make work. And we could do it exhaustively. Exhaustively is where you deliberately just do the possible ones and see whether they work or not. Now, we've boiled a question with 16 spaces now down to a question with only 4, because every other one can rotate from there. So my first thing I noticed was, in order to do this, a way of doing it is to put an L with an L back to back like that, and then we do the same here, an L and an L and an L and an L. Because of where that is, that tells us that that could go there, or it could go there, or it could go there, or it could go there. And if we rotate it round, it means we could also do. So that tells us this one is possible, this one's possible, this one's possible, this one's possible, and by rotation, that one must be possible, that one must be possible, that one, because we could have flipped them the other way around. In fact, not even rotation here. It's by flipping it over, so reflection. We could have just flipped the whole thing and put them the other way around, and the dots would go in the other thing. So that's got all of these, but also by rotation. This is the smart thing about this. By rotation, we've also shown that those 2 are possible as well, and those 2 are possible as well. So that is done all of those ones just from that one drawing. So we didn't even need to do 4. By just doing 1, we've eliminated, or shown that there are at least 12. We've ruled out that answer, and that answer, just all automatically. So the only thing left to do is, can we find a way of putting the dot in the middle? So to do so, I started it off by just drawing one, which would give the dot in the middle. And then I realised, well, the only way to put an L with that is to come out of it like that. And the only way we can put an L out from there, and that does leave an L, and that means the middle one's possible. But by rotation, if we know that this one's possible, it also means that that one's possible, that one's possible, and that one's possible. So we've actually proved that all 16 places are possible for this dot just by doing 2 diagrams. And this is what this is all about when you're doing math challenge questions. There will always be a simpler solution than it originally looks. So it's just all 4 L shapes, 4x4 grid, all 16 cells are covered. And this is the bit, rotated and reflected, and the black dot's visible from both sides. So that means that we can use it both ways round. And I think what we've just shown is that 16 is the magic number for this one. So it's just breaking these questions down. And this is quite a difficult question that we were able to solve. It was no guesswork. It annoys me when I see people saying, oh, I had to guess some of the questions. I was like, well, don't. Just put the ones you can do. The thing about the maths challenge is it's not about getting them all right. I've seen some very gifted mathematicians getting a bit sad or upset because like, I can't do the questions. It's like, these questions are sent for all year 7 and 8 students in the country that are entered into the maths challenge. So the top of the top of the top of the top, like the top 5 in the country would go off to like the national Olympics for maths. So these are qualifiers. We then have the kangaroo and the Olympiads beyond that. So it's really trying to find the top mathematicians. So don't be offended if you can't do it. And if you're watching this video preparing for next year's maths challenge, brilliant. This is a good way of preparing and understanding. You can't get better though by copying. This question won't be in the next one. The copying you need from what I'm doing today is copying the techniques, not copying the answers. And this is the thing that people struggle with. Doing the same answers won't actually help you at all. Learning the answers won't help you at all. The only thing that's going to help you is learning how these questions are attempted. I think we've got one more here. If I press down like that, here we go. So Emily, Krish and Kirsten, irrelevant people really, because it's the largest 2-digit prime, and each of its digits is prime, and the smallest 2-digit prime, and each of its digits is prime. And then subtract and see what answer we get. So the first thing I did was think about, well, what are my prime digits? 2, 3, 5 and 7. They're the only ones. So the only numbers I've now got need to play with are 22, 23, 25, 27. These are the lowest numbers, because remember there's no 1. 1 is not a prime number. Therefore, these are got to be the lowest ones starting from 22. Well, that's not a prime. It says the largest 2-digit prime. That's not a prime. That's not a prime. This one is prime. So we've now identified that the smallest one is 23. Well, the highest one is likely to start with 7. We're going to check them all. 72, 73, 75, 77. Well, that divides by 11. That divides by 5. That divides by 2. Well, 73 is a prime. It doesn't divide by anything. You can check all the timetables. It doesn't divide by anything. That means we've got the 2 prime numbers. We've got the largest 2-digit prime. Because remember, beyond this, they'll become 3 digits. Because 80s, that's got 8 in it. 90s, we've got 9 in it. 8 and 9 aren't prime. So they're the 2 prime numbers. So it's about breaking the question down. And there is your final answer. The gap between the largest and smallest 2-digit prime. But the only way you can attempt these sorts of questions is if you know what is meant by terms like largest 2-digit prime, smallest 2-digit prime. If I was looking at the smallest 3-digit prime, for example, the smallest 3-digit prime starts at 100. So what I would do is I would investigate and the first thing I always do if I'm trying to investigate whether things are prime is rule out the things around. That's the 2 times table. They can go. That's the 5 times table, so it's gone. And then we're likely to start finding primes. And I believe I'm right in saying that that's the lowest 3-digit prime, because we can check the sevens, the 7 times table. We know that 70 so there we go, 98, then 105 and 112. And we can investigate. We know the 9s is 108. The 11 times table goes to 110. The 13 times table is worth investigating. 13 times table, well, we know that 10 times 13 is 130. So if we go down in 13s, we get 117 and 104. So 104 being the 13s. And always worth considering the 17 times table. That would be 5 times 17 is 50, 85. Plus 17 is 90, 102. So that's where the 17 comes in. So these are all primes, but we're looking for the smallest in this little thing. So it's just another way of looking at these problems. Now, in the description below the video, I have posted a link to lots more of these questions with work solutions. I'm happy for anyone to be trying those questions. It can be now, it can be in a month's time, it could be next year when you're preparing for your math challenge. I'd love to find out that people are coming and having a look at some of the questions. Try the ones that I've done on this video. Obviously, I'm hoping people will pause and have a go at them, but then there's even more on there. I'm happy for people to put any question down there and say, how do you do this? And give me a way of getting in touch, or send me an email, and I'm more than happy to contact you and explain how different questions work. Thank you so much for joining me. I've been Mr. Harris. You haven't. Look after yourselves, and I hope you have a wonderful weekend. Take care.